My name is Jaebom, and I'm a senior developer working at Wolfram Research. So today I'm going to give a talk about what's new in geometry. We explore some recent advancement in geometric modeling and computation. So first, I introduce the computational geometry. In Wolfram language, there are many functions designed to analyze and understand geometric structures. We've been continuously adding new capability to work with various geometry regions. So one of the recent features we've introduced a field curve and joint curve. While these were originally just graphic primitives, meaning they were mainly useful for visual representation. Their functionality was limited, so now these curves are deeply integrated into the Wolfram language. For example, here's the demonstration of joint curve, which show the capability of the joint curve added to region. So we define the point, and joint curve now can work with region because now it's region. And then you can compute the arc length. And another one is field curve, which is two-dimensional region. And again, it can be work with region, and also you can compute area. And now let's move on geodesic computation. So essential aspect of understanding the shortest passes on the surfaces. In this section, I want to highlight two key functions we are developing. So geodesic curve and geodesic distance. This function allows to analyze geodesic in various contexts. So geodesic curve function illustrates the shortest path between 2 points on a given surface. Meanwhile, the geodesic distance function, they calculate the distance between those points along the geodesic. So this provides more accurate measure than just straight line distance on the surface. So for example, here I just have some ellipsoid and compute geodesic curve between the 365 and 900. This is the just index of point on Mesh. And you can see the line is written. This actually describes the line along the surface. So graphically, you can see here's 2.36, 365, 900, and you can see the geodesic that connecting these two surfaces on these 2 points on this surface. And also you can compute the actual distance of this geodesic by using geodesic distance function. So here's the distance between these 2 points. Next, I want to introduce new functions that compute the curvatures, specifically the Gaussian curvature of the surface and mean curvature, and also 2 principal curvature, the minimum and maximum curvature. So here's the function called region Gaussian curvature. Like the name implies, compute the Gaussian curvature of the surface at the given point, and region mean curvature, minimum curvature, and region maximum curvature. For example, I got some meshes, and then I want to compute Gaussian curvature at 1. 1 is the index of the coordinate point, which is minus 0.495. And also you can specify actual coordinate. For example, this one, mesh coordinate is like, this is point on the mesh. And then you can compute the same Gaussian curvature instead of using the index. So here's the example of 4 different curvature over this region I defined. And mesh coordinate means you will get all the Gaussian curvature over the mesh coordinate. So I have 4 different curvatures here, and then here show the difference between all these curvature you just computed. So it's just Gaussian curvature and mean curvature and minimum and maximum. This function is still in development. So you you will see in your future version of Mathematica. And moving on, I will talk about advanced mesh processing. There are several mesh processing techniques that help improve the structure of mesh or modify it. For example, the decimation reduces the number of elements in a mesh, smoothing reduces noise and surface roughness, and remeshing improves the shape and size of mesh element. And subdivision defines a mesh by subdividing the element. Now, I will show some functions that perform these processes. The first one is called simplify mesh, which also still in development. And this function reduces the number of elements in a mesh. For example, you have Stanford Bunny mesh. And here, if you see the information, you can see it's about 34,000 the vertices. And function simplify mesh, first argument is the mesh again. And then the 1,000 means we want to reduce the number of points of this mesh to 1,000. And if you apply it, then you can see a little bit more, much simplified version of the bunny. So if you see the information, I cannot see where this is have 1,000 points. And also you can notice that even we reduce the number of points, you still see the bunny. It's trying to maintaining the essential structure. And here's another example. I just changing the various, the number of points I want to. So here 4 different steps, 1,800, 400, 200. If you check it, you can see the different simplification here, 1,800, 400, 200. This is much simpler than the original input, but it's still maintaining the shape. And next, we have function called smooth mesh function. As the name implies, this function smooths the mesh by removing noise. So, for example, here I just construct mesh boundary discretized region using boundary region over CS region. So this is boundary mesh region, which have sharp edges alongside, and just apply smooth mesh. You can see more smoother version of these meshes. Again, this smooth mesh has various arguments you can apply. So for example, here I just gonna use expression method with different iteration, 5, 10, 20, 30. And you can see if I run only 5 iteration, this is result 10, 20, 30, you start getting more, smoother result. Also, this also is in development, and we trying to add more, options for fine-tuning of this processing. And I don't show here today, but we also working on remeshing and subdividing functions, which giving the nice mesh processing. Okay, next we are talking about the modeling. There are several methods you can use to model regions, including the geometric region with basic meshes, which is very basic, like a mesh region and bounded mesh region, and constructive solid geometry for like CAD-like construction, and using implicit representations. So, and then another method could be the combining and transform the region to create new ones. And then, so one of the things we are working on is introducing the library of pre-made geometry, which to make modeling a little bit easier. For instance, you can easily create models of screw and nuts by typing the specific name here, like geometry model. This is just temporal name. And then you can specify like a metric hex socket head cap screw, metric hexagons in nut. And then you can see the various, nut and bolt that getting from the library. And from this library, you can get the actual region by applying the region method here. And you see here's the screw and nut and washer. And at the end, using the CSC region, you can combine this bolt and nut and washer together. Here you get a nice, CSC region. And also, using the translate or another operation on it, you can actually have this final result. Looks like some table with bolt and nuts. And the another thing, the CSC region, the new feature we added to CSC region is supporting annotation. The current version of Mathematica, we add style to CSC region. So you can add style to the region inside the CSC region, like this case is, so first element is some of green color, pink, and here's the result. As you can see, you see the outside and inside, and then this face all have different colors. So easily can be distinguished by this color, the CSC region. And in addition to just style, we add more annotation. Like you can add some custom annotation over it. So for example, here I just define CSC region with annotation. This is user-defined custom CSC region. So A equals 100. So you build CSC region. Also, you can apply all these annotation function. For example, in this case, I want to get what A in this CSC region, the second element, then you can return 100 like we specified. So if you check the option of this CSC region, you can see now there are annotation rules applied, it like a user-defined annotation like we did here. The second element, A is 100. So you can specify another value A to this ball also, etc. So if you're interested in learning more about the development CSC region, there will be a talk right after mine by Alec, where you will dive deeper into advancement and application of CSC modeling. And here's another addition like that I mentioned earlier of this talk. The field curve and value curve now deep inside in region. That means field curve can be used. You construct the CSC region, especially for 2D case. For example, if you have this field curve, let me just show you what it is. And then you want to construct some CSC region using this shape and a rectangle, but I do the intersection operation over it. Then you can see probably around this area, you now have a nice 2D CSC region combining this field curve and rectangle. Okay, now I'm gonna discuss about the modifying existing region. There are many methods, but one of the functions we try to add is called linear extruded region. This function allows to take two-dimensional shape and extend it linearly along a line, effectively creating the three-dimensional region. So for example, I just get the random polygon and convert it to mesh. And if you do linear extrusion through the region, this one over, not over, the 1/2, this specifies the length of side. Then you got the nice shape, 3D shape out of it. Also, this can be applied to like the special region like rectangle disk. For example, if you learn this function over rectangle, same 1/2, you will get a cuboid. This is pretty basic. And then if you apply to disk, you can see this easily become the cylinder. And we, alongside with this extrusion, we also adding another function like revolving. So now when you have line or two-dimensional shape using the function, you can create like some 3D, some revolution of the surface easily. So you can get the 3D surface or solid region using those functions. So I cannot show the example today, but yeah, that's one of the things we are developing. And the last section, I'm gonna just briefly cover splines. We have various spline functions available, such as B-spline surfaces, B-spline curves, and Bezier curves. These are all piecewise polynomial parametric curves or surfaces that allow us to create smooth and flexible shape. So we adding this spline surface or curve as region, like I think last version. So this can be used with the geometry functions now. And currently we are developing the function called like a boundary splines region. What this function does, I mean this constructor, allow us to construct solid mesh region based on specified faces, like including the B-spline surfaces, edge faces. Like a mesh region only allow the face, like polygon. But by allowing these B-spline surfaces, the result in a smooth bounded solid region rather than just flat line surface. I mean, the linear surfaces. So, but I don't have specific example for boundary spline surface, I mean, region today. But like I said, its function is currently under development, and you will see it in the near future. And additionally, many of the features I discussed today are also being enhanced, so stay tuned for even more capability in geometry modeling. So this is the end of my presentation today. I encourage you to check out additional talks that you can attend. Like I mentioned, the first one focuses on modeling with the CSG region, Constructive Solid Geometry Library, and will take place at 11:30 right after this talk. And there are another office hours on Friday, 3:00 p.m. So if you have any question about discrete computation, that including the geometry and number theory, etc., or even the graph, so feel free to join us for any inquiry you might have. And lastly, we have a YouTube channel, the Wolfram R&D channel, which feature many live streams on geometry and some overall development in Wolfram R&D. So please subscribe to the channel. It's the youtube.com Wolfram @WolframRD. So thank you for attending this talk. So if you have any questions, feel free to ask. We have about like 10 minutes. Yeah, I will post this slide that I present today, but most of function you cannot evaluate. That just take a note because it's still under development. You can still see the output, but yeah. But I will definitely, yeah, adding this to this talk. Area of a polygon on a sphere, you mean like that the polygon defined by geodesic fitting point? So not specific function, but if you embed the polygonal sphere in whatever way, you can discretize it, so you can get the approximate the area of the polygon, I believe. So for now, what I showed today, actually just using just giving the example on the mesh. So this geodesic function that I show based on the mesh structure here. So you see this is not the smooth curve, but as you can see here, this line all along just passing through this actual the polygon, I mean the triangle with your geodesic. So it's not smooth curve by say, because this is not smooth surface. But this is case of mesh region. We plan to add, yeah, like we said, differential equation, other cases like implicit cases, or even like some graphic primitive. Those cases we plan to add specific the function probably as output using the like a differential equation you mentioned. But the example here is more like a discretized version. So for a lattice of three-dimensional hexahedron prism lattices or any other kind, is it possible to create and find properties like neighborhood of prism or network connectivity of the bigger mesh made of those smaller prism? Yes, I think. So for example, we have like a function called some getting the graph out of mesh structure. So what is called? I just forget the name of that function. But yeah, once we get that graph that is by structure of mesh, then you can easily find the neighborhood using the function. I mean the graph. That actually just describe the connectivity of your mesh. And actually, this process is more like a graph analysis. So for example, you can even find connectivity of bigger mesh made of those smaller prism. Like you can check the sub isomorphism using the graph you have also, etc. Oh, the function I mentioned is mesh connectivity graph. Oh, defined by geodesic curves on a sphere. Yeah, it's possible, but like I said, we don't have a specific function to compute for now. But I don't see why not. It's just matter of fact, we cut out those area. But I think it's possible. For importing GLTF or GLB format, as I know, it's under development, or I'm not sure it's already development. That is not my area. But if you want to know more about those portal, you can attend the Friday the office hours, the discrete discrete computation. What do you call it? That office hours, you can get the answer for that questions, but I'm not exactly sure for now. Yeah, discrete computation office hours Friday. You can ask that question again there. Okay, so it seems like if there is no more questions, so okay, we have 4 minutes, but yeah, I think I can wrap up the talk today. So thank you for attending talk. And if you have further questions, feel free to attend the discrete computation, the office hour, Friday, 3 o'clock. And if you have, like I said, want to know more about CSG region development, please attend the 11:30 talk right after this talk. Oh, last question. Yeah. Yep, thick surface extrusion. Yep. That's still supported. It should be. Yeah, method extrusion. Yeah, that's still supported. Okay, again, thanks for attending this talk.